Perfect. All right, thanks. Yeah, so thanks, Nathan, for the introduction. And yeah, I just wanted to talk about some machine learning methods and directions in high energy physics. And so as I was kind of discussed this morning, things have come a very long way in the last few years. So I was looking at some notes last night from the first analysis ecosystems workshop, and it was mostly BDTs versus neural nets and neural networks, and is TMVA any good anymore? So things have come a very long way since then. So this will be mostly a methods overview talk. And since it's an overview, I think it's important to say a bit about who I am, because all of my examples are biased towards that. So currently, I'm working on this machine learning initiative at Slack, which is just kind of a cross-experimental kind of consulting for different experiments. And so I do have, on the physics side, the projects I'm working on are Dune and Magis, and mostly with that, it's differential simulation, and then also these sort of implicit models and scene representation. But I did my PhD on Atlas, and so a lot of my examples will be biased towards sort of Atlas LHC, and I did Dix4B and some fast colorimeter simulation. And so personally, I kind of want to bring some of this cross-experimental perspective, but then also, provide a sort of an entry point and promote some discussion for some of these methods. Again, my perspective is very limited and biased. So there's this nice HEP ML living review if you want to see a living list of some activities going on. And so that said, at least in my view, an overview of the landscape of ML and HEP is kind of these 6 areas that I highlight here. Again, these are areas that some of them I chose because they're very relevant to me. But that said, the place to start, I think, is with these standard techniques. And so by that, I mean, I guess kind of 2 things. So one is the standard use of ML and HEP, so the way that people actually, use ML. And then the other is standard ML methods, but maybe ones that have found some new use in high energy physics. And so the big case, of course, in especially LHC stuff is classification. Again, this BDT and neural network stuff, and these are usually pretty simple neural networks. And in this case, too, sometimes people extend these by parameterizing them in stuff like resonance masses for resonance searches. But yeah, again, pretty simple. And so these are done in analyses. For instance, I cite some examples from Higgs because that's my background. But then also in stuff like flavor tagging or beat tagging, these are used, in this case, you have some low level information, you aggregate that with a BDT or neural network into a higher level tagger. So these are pretty standard. We've gotten a lot of mileage out of just these very simple kind of classifier architectures or these models. So to keep that in mind, there's also some kind of classical ML stuff that is used, but only kind of sparingly. So Gaussian processes, for instance, are a good example of this, where Gaussian processes are used. I have a couple of examples there for a smoothing, and then also an interpolation systematic. But again, very classical ML, not used super commonly in HEP. Another thing, for instance, is bootstrapping, bootstrap resampling. So that's done in my analysis for an uncertainty, but then also similarly for beat tagging, there's this Monte Carlo statistical uncertainty that's done with bootstrapping. And again, very classical method, only used sparingly. And I mentioned also this neural network reweighting, which is done with very simple models. And there have been a couple of papers in recent years on that, including, again, my analysis. So there's the bias again. But when we think about kind of going beyond these simple architectures, these simple BDTs or neural networks, one of the first things that people do think about is trying to encode some physics information into this. And there's been a bunch of work on this and kind of 2 areas. So one is how do we encode this into our architectures or losses? Then the other is kind of this area of simulation-based inference, or including a physics simulator in our machine learning loop. And so on the architectures and losses side, the big buzzword to use here is inductive biases. So there's this nice deep image bias paper that I linked to there that does this for convolutional neural networks. But basically the idea here is that we have all these, a bunch of different architectures, and each of these architectures can take different forms, which encode various assumptions about the data set of interest that we like. And these, I know in particular, graph neural networks, and there's this nice overview there. There's been a lot of hype about that in particle physics over the last couple of years, transformers as well. And then one of the other cool examples, I think, is these energy flow networks, and then an application of those in flavor tagging as well, where the idea there is you do your machine learning on sets. So instead of, a lot of times people would take a bunch of particles that had no order or anything a priori, assign some order, and then use an RNN. But if they have no order a priori, we should be encoding that. And so that's where this ML on sets comes in. And then on the Dune side, or focus more on neutrino side, this liquid argon TPC paper and this end-to-end reconstruction. The big thing here is relying on advances in computer vision. So for instance, this particular paper uses ResNets, which are, again, a particular computer vision architecture. And then also graphs are in there as well, encoding this particle physics assumption. So I mentioned also there's the simulation-based inference. And so this is having the physics kind of in the loop. There's this big paper, Frontier of Simulation-Based Inference, that has a bunch of different ways that people do this. But in practice, people, I don't think, do this that often. So I cite one example there, but don't really see too many others. So maybe that's a question of why don't people do this? But then the other thing is in this simulation-based inference framework, usually the simulator is used as a black box. So we only take a look at the inputs and the outputs. And so how do we get beyond that? Nathan, do you know the answer? I think we do. The differential programming is sort of the next step in this kind of progression of where we can take exact physics code, or physics code that we as physicists write, and then we can do fun stuff with gradients and with optimization. And there's a dedicated talk on this by Lucas afterwards. So just next. So won't go too in detail. But again, the idea here is to write or translate your physics code in automatic differentiation frameworks. So this is stuff like PyTorch, JAX, and TensorFlow you might be familiar with. And when I say automatic differentiation, I mean we automatically get gradients with respect to code parameters. So automatically there is very loose term, but we can talk about that later. But this opens up a lot of possibilities. So we can do gradient-based optimization of parameters of our code, and we can also chain together physics code with neural networks and do a training like that. So that's really nice. There are a lot of promising ideas here. So I think there's some discussion later on the detector optimization, which I linked to mode there. Also calibration a lot more. So I have here a couple of examples. Got to flatter the conveners of the session a little bit. So MADJAX is differential matrix elements, and then NEOS for differential HEP analysis chains. So shout out to Nathan and Lucas on that. And then I also, some of the ongoing work that I'm doing is doing this differentiable programming in a liquid argon TPC simulation. And so again, still ongoing, but mostly brought up to have the point that this is being discussed in other areas as well. So I think a very cool topic. And one thing that kind of interacts with the topic of differentiable programming as well is how are we thinking about and representing our signals? And that's where this other area comes in with these implicit neural representations. And these are very, very new, I think, to HEP, or at least people aren't thinking about them a lot, and that's why I wanted to bring them up. They're mostly being used in the context of something like scene representation. And the idea here is to parameterize signals as continuous functions using neural networks. And so these are also known as coordinate networks. What you do is you put in to the neural network some space-time coordinate, and then you get out your signal or whatever parameter of interest at that point. And so in high energy physics, one of the things that people do a lot is use a voxel representation. So you have some gigantic 3D space, you bin that in some way, and then that's how you represent your 3D signal. But then if you have a really big space, or you need a very fine resolution, then you're limited by your voxel size, or the number of voxels blows up. And so using something like these implicit neural representations can be very nice because one, the network scales with the complexity of the signal, so not that size or resolution of your bin space. And then two, these are tunable because these are neural networks. And so that's really nice. You can do stuff like train on simulation and tune to data. And so in particular, again, sorry for citing my own work more, but so this will be on archive hopefully in the next couple of weeks, but this photon library parameterization here, this photon library is part of a liquid argon TPC simulation. And the big thing here is that it's very, very expensive to simulate, and especially once you go to a larger detector, for instance. And so the idea would be to simulate this once and then have a very nice model of it and that you can do a bunch of fun stuff with. And that's what we do here, is representing it with a neural network. And this is also more efficient parameter-wise too. More sort of along the lines of this scene representation stuff that I've talked about. There's this light field sensing array thing that I've been working on, where the idea is to go from a set of 2D images to a 3D model, where the 3D model is represented by, again, these implicit representations. So kind of cool. And again, not very much used in HEP, so keep an eye out. So these top four kind of all interact with each other, very nicely. But then I wanted to talk also about these bottom two areas, which are very large, but also you can think about those interacting with the rest of the ecosystem as well, very much so. And so generative models are the first big area. And so again, very large, but the goal here is to learn your distribution of training data, and then you can sample from that to get outputs that kind of look like your data set. So these are GANs and VAEs you probably have heard of. Just to mention methodologically, there's newer methods like normalizing flows, which have gotten a lot of traction, I think, in the last couple of years in the HEP community. And then there are diffusion models as well, which have gotten a lot of traction in machine learning, but not so much in the HEP community. So maybe something worth thinking about, just to put that on your radar. But some examples here, so they're often used for things like direct parameterization. So I have the calorimeter shower simulations, so with normalizing flows, and then also VAE and GAN examples. But these are also very versatile. There's a whole class of anomaly detection algorithms, for instance, that use generative models. Or there's this differential simulation surrogates where you use these generative models to get gradient estimates for a non-differentiable simulation. So again, very useful, very broad fields. And so just to mention that. And then the other big area that I wanted to mention was uncertainty quantification. And this is kind of twofold here. So one being, how do we put error bars on our predictions? And this is very important, obviously, for HEP. But I think this is also very much an open research topic. I don't think we really know some answers to questions like, how do we know if our uncertainties are correct, or how exactly and when exactly we assign them? So again, something that I think is very, very much an open research topic. The other thing that has been worked on, though, quite a bit in the last couple of years, or at least somewhat in the last couple of years, is how do we incorporate or deal with uncertainties in training, stuff like machine learning classifiers. And so there's this inference-aware learning, so Inferno, and uncertainty-aware learning. NEOS, which I mentioned a couple slides ago, also does this. And then one of the classic examples of this is this learning to pivot paper that I cite here, where basically you learn your classifier adversarially to make it insensitive to some nuisance parameter. And so that's kind of my whirlwind overview of the landscape. And I would say that these left three areas here of incorporating physics information, obviously the standard techniques, and then generative models, these are around. People know these, people use these even, but there are still some exciting directions. But again, they're part of the community. And these right three, so differential programming, implicit neural representations, and uncertainty quantification, these are kind of newer. People are talking about them. Obviously, there are more sessions on automatic differentiation, for instance, today. But these are the things to kind of keep in mind as the new frontiers maybe moving forward. And so since this is, of course, the analysis ecosystems workshop, I wanted to talk about some frameworks. And there's some nice discussion also in a variety of places, for instance, what I linked to there. So of course, Python is the go-to for most people, I think, for machine learning. There are all these nice tools like PyTorch, TensorFlow, and Keras are very, very much around. I think JAX is becoming a lot more popular in recent years, and also has some nice JIT compilations, so people like that. For stuff like BDTs, there's actually Boost, which actually is not just Python, I learned this morning, but is very often used in Python. And of course, scikit-learn, people know and love. But then also entering the conversation is stuff like Julia. There's some nice automatic differentiation tools for this as well, like Zygote is one of the big examples, but also compiled language, so people like it for scalability, and et cetera, so on the radar for sure. There's, of course, the C++ and root kind of area of things as well. And TMVA is still used and still around. So, keep that in mind, I guess. I don't know that people like that it's still used and around, but it is there. And then there's a bunch of nice tools to kind of go back and forth between these, which, I think we all very much know and all very much love. And so with that, I just want to close with some points for discussion. So the three kind of big areas that I thought of when I was thinking about the main challenges for machine learning and high energy physics are these areas of scalability. So how do we balance functionality with memory and computing costs? Like if we make something differentiable, so use one of these automatic differentiation frameworks, what does that add? onto our overhead in terms of memory computing. Interoperability, of course, so how do we keep ease of use for methods developed outside of the community? If somebody has a GitHub repo that they publish with their paper, can we use it right away for HEP? And then also just discovery of like, okay, machine learning is a huge field on its own. How do we keep cross communication with the ML community? And how do we sort of stay cutting edge? And so that's all I have for today. Thank you very much.
Thank you very much, Sean. And I'm sure you have loads of questions for Sean's, but I must exercise my right as convener and completely cut you off. And we need to speed right through the next talk to make it to lunch.